would be about y and minus 1 derivative. It would be y and minus 1 at x naught equals just some other name, sub-0. So not so much in section 4.1. I think I started talking about 4.1 before the test, I feel like, is when I drew that spring mass. Yeah. Is that something there? And I haven't gone back to that, so if you're, yet. But if you're thinking, well, I'm trying to work on the homework, this doesn't look anything like what she's talking about. What I'm talking about now is in 4.2. So the whole structure of the solution and what sort of initial conditions can be imposed and so on. This is just the groundwork, and then we'll go back the whole rest of our time in chapter 4. It's going to be about the spring mass. So we have plenty of time to accept the harmonic oscillator, or whatever the heck it's called. So for now, we're kind of talking about the theory. And what about the structure of the solution? I'll write it over here. I didn't plan this well. Did I leave that whole part blank? Form of solution. YG, YP, plus YH. Our book is going to call this YC. That up here. So the YH, aka YC. Can we go to a finer level of detail? What about the YH? How many terms will be in there? N, whatever the order of the differential equation was, that's how many terms will be in YH. And the notation for these is, so the breakdown of YH is into Y1, 2, 3, 4, etc. And this is where all the C's are in the solution. Cn, Yn. Okay. And then what's the special? I'm about to diagram this like I was in a grammar class. What is the thing that the YP does? In star.
Left hand side equals right.
Okay. So the brain. I'm just checking the brainwashing. Left hand side
Equals
right hand side. And then initially, how we were describing the YH is we were saying the YH makes the left hand side equal 0. And then yesterday, since we're now on the higher orders realm, not only does YH zero out the equation, each of the Y's one by one does, without even the C's attached. So Y1 by itself, Y2 by itself, each makes the left-hand side of the equation equal 0. And then because the equation is linear, if we multiply the C's, the Y's times the C, the ones that made the left-hand side equal 0, they're still going to make it equal 0. They're going to make it equal C times 0. And if we add them all together, they're still going to make the left-hand side equal 0, because it's going to be 0 plus 0 plus 0, etc.
What about a combination of just, let's say we're in the nth order, and you just use 2?
That's a good question. If you just use 2, like say we're doing a third order equation and we only have a C1Y1 and a C2Y2, is that what you're asking? I'm so glad you're asking that, because when I tell you what the answer to that is, you're not going to like it, but you asked the question. So the problem that will happen, so the thing that you're having to check, kind of without being able to show any work, is the number of terms in YH, does that agree with the order of the equation? If we only find, say, 3 of those Y homogeneous terms, and the equation is 4th order, there's, first of all, no guarantee that we have a unique right answer given initial conditions, and somebody else can find for us, like, it's out there whether we see it or not. The Y4 is out there waiting for us to find it, like the little orphan standing on the street corner. Wait, I have to go in there too. So the general solution really means it encompasses all the possible solutions there could be. So if we only found part of the YH, we would say we found a family of solutions, but it's not the general solution. So when we reach the point where we're expecting a certain number of those YH terms and we don't have enough, we're gonna have to work very hard to find the missing ones. And it's not pleasant, but we have to find them all, so we wanna get the entire solution.
Pokemon.
The unfortunate thing about that is, for differential equations, that's a bigger deal. So what that's analogous to in calculus, like in calculus, when you first learn how to take integrate integrals, your teacher would be kind of a jerk about whether or not you put that plus C in your answer.
Yeah.
But that plus C was the Y homogeneous. You were leaving off the YH. Even in calculus 2, when you did trig sum, partial fractions decomposition, 16 rounds of integration by parts, you do some crazy integration question, and you forget the plus C, your teacher was still zinging you. Especially if I was your teacher, I hated it. It broke my heart, but I'd still take the pointer away from you without the plus C, because the YH is in there to help us satisfy any extra constraints that are given in the physics of the problem. Okay, so how our math is I'm gonna give us another couple examples today where we just verify that we have YG or YH, as the case may be. And I feel like one of the last words I said to you yesterday was the word Wronskian. And that bears some more work here. So for the YH, let's see, so I did write that in a really stupid place. So let me put next to the YH, I'm gonna put a star. So this is for the YH part. So for the Y homogeneous, the number of terms has to agree with the order of the differential equation. Each one of them individually has to make the left-hand side equal 0. And what was the third thing that those YHs had to do? They have to be linearly independent of each other. So in the YH, so Y1, Y2, YN must be, the phrase is linearly independent. And it's actually okay in our class, if you just say independent, it'll be taken that you mean linearly independent. So with those linear algebra and differential equations, you could abbreviate that to independent. In statistics, they use independent in a different context, but in calculus-based math, it'll be understood. And our test for that yesterday was that weird thing called the Wronskian. That was a beautiful face you just made there, Mariana. All right, so I'm going to give us another example or two, but really we're going to quickly not have me making these up in my head because it's giving me a bit of a headache. So I'm going to give us an equation and a YG, and we're going to try to do all the verifying. And that's pretty much what you're going to see in section 4 too. But then really it's going to fall on us to solve a given equation. So, you know, by the time our test rolls around, I could be giving you a 10th order equation. And you're gonna go out there and you're gonna find YG in some finite amount of time. And when you're out there looking for the YG, you're kind of thinking, I need to find Y1 through Y10. Those have to be 10 independent functions that make the left-hand side of the equation equal 0. And I have to find a YP. And when we look for these things, that's typically how we solve a higher order equation. We don't necessarily try to solve the whole thing holistically. We deliberately go out and say, I'm gonna first try to find YH. That's usually what we do first. And then as a separate matter, we then go out and try to find the YP. And the reason we do it in that order is we're gonna have several different strategies for trying to find the particular solution. And several of the techniques for finding Y particular, they use the Y homogeneous to create the YP. So that's kind of the order that we go in. But for right this moment, we're just gonna, I didn't put the star. There. I'm gonna give us a couple of equations and we're gonna check solution to solvingness or whatever. I'm gonna give us an equation, I'm gonna give us something for the solution, and we're gonna check whether it works or not. Meaning it doesn't meet all the criteria. And then maybe as a warm-up, we'll try a second order. So verify and now we'll give us an equation. So yesterday, did we do a problem that had an x squared in front? Okay, so how about for this one, I won't put an x squared in front. So how about y double prime minus 2y prime plus y
¿Te vieras como que si vas a una escuela católica?
who cares? 17
Harry
at this
Potter.
point. So I'm gonna write down a candidate for the solution and we're gonna check it. So for this equation, we're gonna verify that YG is, doesn't actually matter if you write the YP first, but I will. Plus C1 e to the x plus C2 x. So we're gonna try to check that. And in a few short days, you're gonna be finding that your own dang self. At least the YH. Right. So what we're doing here is we're not gonna go at this thing with a blunt instrument. Meaning, we're not gonna take the YG as a whole and sub it in. If we did take the YG as a whole and sub it in, it should make the two sides equal. But we're really not just checking, does this work? We're checking, is this the general solution? So we're gonna check the YP by itself, the Y1 by itself, the Y2 by itself, and the independence. And then in your homework, after that, he's then gonna give you initial conditions and help you find out what the C1 and the C2 are. I don't have the energy for that, so I'm not gonna give us that. So who's YP?
17.
17. All right, so we say, this is YP. If all goes well, it should make the left-hand side equal the right-hand side. Just so I don't take up too much word work. I'm gonna write down the equation, putting in question mark over the equals to remind myself that's what I'm checking. For the Y, I'm gonna put 17 minus 2, what's the derivative of 17? 0. This is so ridiculous, I'm gonna write right over that. Plus the second derivative of 0. 0.
Beautiful.
Check, that's all the YP has to do.
She
Work
meant
in
to
the
say
equation, I
second
don't care how
derivative
small
of
or large
17,
you are.
not 0.
Think, that's
Maybe
YP.
the first derivative.
And then separately, one by one, we want to check the y1 and the y2. Do they make the left-hand side equal 0? And so I've never really come up with a good way to ask this question. Does this have enough terms to be YH? Yeah. Second order, there's 2 of these. So that one, I don't really know how much we would write down for that. We notice that. So then the y1 is e to the x. y1. So y1 is e to the x. Actually, for that one, I think I can also just try to sub it in. And when we sub that into the equation, we're not wanting it to equal 17. We're wanting it to equal 0. So I think for this one, we can even start at the beginning. What's the second derivative of e to the x? E to the x, so more. You could leave the c1 attached, but we don't. The fact that we can attach the c to the y homogeneous, that's part of linearity. So that first term in the equation is going to be e to the x minus 2 times the first derivative, x, plus the y itself, e to the x. And then we're asking the question, does that equal 0? Yes. So y1 is doing its job. And then y2 is the one that's going to need a little more space, because for y2, we are going to have to use the derivative product rule for derivatives here. So this is y2. And then, okay, I was going to try to just sub it in at the same time, but I won't. So y2 is x e to the negative x. What is y2 prime? X e to the x plus e to the x, which, not that this is going to help anything, but that's x plus 1 e to the x. And now let's do its second derivative, and then we'll sub the whole thing in. So y2 double prime, x plus 1 e to the x plus the derivative of x plus 1, or 1, yeah. So that's x plus 2 e to the x. And then we sub the whole thing in. And while we're subbing the whole thing in, we're subbing the whole thing into this equation, and we're trying to get, does it equal 0? So the e to the x, I think we can see, the e to the x is going to be common to all 3 of those. I might even just factor it out so that my check doesn't look so picky. So e to the x, I will factor it out. The y double prime has an additional x plus 2 factor. Minus 2 times, and then the y prime has an extra x plus 1 factor. Plus, what about the y term?
1.
X. So the y term has that x. All right, please tell me that's all going to 0 out. Yes. So far, so good? All right, so the third thing to check, so we checked the cardinality, the number of terms in YH, it was 2 as expected. The Y1 and the Y2 did their job, they zeroed out the equation, and I think today I may mention a different way that we interpret that. And then the final thing to check is if those 2 solutions are independent. And on the face of it, if I compare e to the x to x e to the x, I feel like they're not different. If you catch what I'm speaking, I'm not speaking mathematically, but they both have e to the x. They're not that different from each other. if you catch me. However, they are different enough. What would be dependent would be if y1 was e to the x, and the y2, instead of being x e to the x, what if the y2 was 3 e to the x? What if y2 was 3 e to the x? That really isn't any different from e to the x, especially since those are the terms that have the c in front of them. So 3 e to the x, it's all a blur to us. We're like, whatever, it's a constant times e to the x. This one is bringing something new to the table. It's bringing that x. But rather than have you try to do a song and dance about, look, the x is contributing, or whatever, we do the Wronskian. We just do the computation of the Wronskian. And I think, so generally when I leave school, that's it, I don't think about you again. But I did think about you for like 1 second yesterday. Because I think by just impulse, I wrote the Wronskian, I wrote the note, did I write a capital W in here yesterday?
They use the books.
I just wrote the word Wronskian, okay. So then, okay, maybe I shouldn't have thought about you. So the Wronskian, the notation for it is capital W. So this is, in a screwball sort of way, this is a function. And what the function inputs is 2 other functions. And what it outputs ultimately is a yes or no. These functions are independent or they're not. And so we feed it the 2 functions. And the math we do is kind of like part of a cross product. If you have some calculus 3 exposure. And it's a determinant if you have some calculus, some linear algebra exposure. So we're gonna do that linear algebra thing, AD minus BC or some screwball thing. We're gonna cross multiply, and then the default is we multiply down and to the right. And then how does it go? Down and to the right. Minus. Left across. Y1, Y2 prime. Minus, and then we go the other way. Minus Y2, Y1 prime. And that quantity, how that quantity checks for linear independence is if we get the actual number 0, that means the functions depend upon one another. One of them is kind of like leeching off of the first one, something like that. If we get anything else, they're independent. Meaning, if we got for this answer, say we did the math to this, it's not going to come out like this for this one. But what if we did this math, and this math came out to equal x minus 2? You see how I would be tempted to try to solve for x and get x equals 2 or something like that? So that's not what we're doing. If we get any answer other than the number 0, we say these functions are independent. So yesterday I wrote that triple equals. So I'm going to write it again, but darker. So the way to say mathematically what I just wrote is if we get anything other than the number 0, so if we get anything that is not identically 0, the functions are independent. So that means independent. So don't be tempted to try to solve that and figure out what x's will make it equal 0. That's not really the issue. And I think some of you who maybe have had some linear algebra exposure were already starting to worry, what if we had a third order equation and we had to do the Wronskian of 3? Or we will today. All right, we're starting easy. So let's try this one first. So for this y1 and y2, let's actually check the independence of those 2. So we're going to do the computation of the Wronskian of e to the x and x e to the x. And the order of these doesn't matter. You can put either one first. The effect that will have on your answer is the signs will be reversed if you switch the two functions, but that won't mess up whether the answer was going to be 0 or not. And maybe one thing I'll say about the Wronskian, in chapter 4 and again in chapter 6, we're going to see some crazy formulas for some crazy computations, and they'll have that W showing in them. So not only is this W, this Wronskian, a way to check for independence, it's useful for finding Y particular in a weird screwball sort of way. So, blah, blah. E to the X. I quickly volunteer to fill in my column there. And then I give you X e to the X. And the derivative goes here. Actually, that's that first term right there. X plus 1, e to the X. And then the math we do is a little cross multiply. So when we do this product, we're going to get x plus 1 times e to the 2x. All right. X plus 1 e to the 2x. And then minus, and we jump over this way.
X e to the 2x.
X e to the 2x. That, so we end up with just 1 e to the 2x. And it's not wrong to just stop there, but, and I know I was probably like this as a student also. I didn't really want to write too much in case anything I wrote was wrong. So I would try to just stop like a sphinx. I'm not saying this, so, but I learned eventually to just accept it if occasionally I'm wrong, because I understand better. I'm looking at this to ask myself, is that identically 0? No, it's not. So the functions are independent. So y1, y2 are independent. And that was the third piece of the puzzle. So we checked the number of the YH terms. We checked that they each did their job and that they're different from each other. Lovely. Third order? Okay. For the third order equation, so what time is our class? And I'm so confused every day. 55. Oh, we have plenty of time.
Yes.
I'm going to be mad at you for being honest. So let me give us a third order equation, and because the thing I want to focus on is the computation of the Wronskian, I'll just give us a homogeneous equation. I'll give us one that doesn't have a particular solution, or if you want, the particular solution is 0. So how about y triple prime plus y double prime plus y prime plus y. I put a lot of thought into this. I actually did. So there's the equation. And now I'm going to try to give us YH. So in this case, since this equation, it's third order homogeneous, its YG is YH. I can say it this way. So the equation itself is homogeneous. So in this case, I'm always kind of thinking I'm trying to find the general solution, but really all that means is we just have to know what the homogeneous solution is. If you want, that means the particular solution is the number 0. I'm going to show it. Okay, so I'm going to give us the YH. verify maybe just the independence. Well, let's maybe verify. YH, C1, e to the negative x, plus C2 cosine x, plus C3 sine x. So there's three of them now. So how about if we just check the E and one of the two trigs? Because when we see what happens with the trig, wait, I'm gonna E right. For the two trigs, because of the symmetry of how the sine and cosine's derivatives behave, the math is gonna be the same for the other trig. So maybe try the E and the cosine, and just tell the sine we trust it. So here's Y1. Y1. And we're gonna sub it in and check that we get 0. So Y1, that's e to the negative x, plus Y1 prime, negative e to the negative x, plus
E to the negative.
okay, plus Y triple prime,
Negative.
negative. And yes, that equals 0. And then after the fact, like, when I first write that down, I'm secretly thinking I just want to go home and take a nap. But then I'm thinking, oh, I wonder if they'll think I'm a genius that I just made that up. But then when I check it, big deal, I think, obviously. And then 10 seconds later, oh yeah, they're just gonna alternate. Now let's check maybe just the cosine. So for the cosine, will be Y2. So we're going to check this. So this is going to be plus cosine x. The derivative of cosine minus sine. The derivative of negative sine, negative cosine. And then the derivative of negative cosine, positive sine. Yep.
Yes.
I guess I should check mark. And then similarly, the verification of Y3 is left to the reader. Whatever, you do that on your break or what have you.